Okay, well, before I got a chance to do what I was going to do, somebody came up with a little plastic BB, dropped it on the table, and had it bouncing, said, "Is this simple harmonic motion?" And we discussed what was really going on there. So you have a BB, you drop it to the table, it comes down, it bounces up, comes down, bounces up, comes down, bounces up, right? So if you observe the height each time the baby comes to rest, you can then find the time interval for every drop and every rise. And I should probably say every fall and every rise, right? Okay. Now, how do you find the delta T for every rise and fall? Well, between collisions with the table, it's in free fall. Okay? Acceleration is negative g times your j vector, if the j vector's, if the y-axis is up. Okay? Acceleration's constant. Okay? This is not SHM. Which requires net force equals negative K x, right? Not even close. Uniform acceleration. Of course, the thing I keep stressing is I'm going to be very unhappy if anybody tries to analyze anything regarding simple harmonic motion using the equations of uniformly accelerated motion, which don't even remotely apply to this situation, right? I'm still seeing people wanting to do that because, of course, it's kind of a habit to go to your equations of uniformly accelerated motion. Hopefully not a habit you picked up in this course, but in your between this course and your engineering dynamics course, you get in the habit of just going to those formulas, right? I understand why, but they don't apply to simple harmonic motion. Very important conceptual idea, right? Okay, well, then we get to the question of, okay, I posed the question, what's the average force on the tabletop, okay, for the time interval from the first drop to the last collision, and I'll say through the last collision, okay? Now that might not be the most logical time interval to analyze, depending on what you're trying to get to, but you can certainly answer the question, right? How do we do that? Well, it took us a while because people say, oh, use energy. Well, the idea of using energy, well, let's think about it. The thing is in contact for a very short time with the tabletop, right? And it bounces because it compresses and then decompresses, right? Now, the compression and decompression is not exactly a linear, does not exactly involve a force that's linear with respect to its position, okay? But it kind of has that nature. The more it compresses, the more force it exerts in the opposite direction. And as it decompresses, the less force. So the force goes up and down. Maybe not perfect linear curve, and we don't know what it is. It depends on the shape and to some extent on the material of that plastic BB, okay? And it's a sphere, and that's not going to give rise to perfectly elastic, to a perfectly linear restoring force, but you are going to have a restoring force, okay? It's just going to be more complicated than that, and in your strength of materials course, you'll probably develop the techniques to actually analyze what those forces would be. What's the compression force on a sphere of a certain material, okay? Maybe you won't, because it's more convenient to use multivariable calculus to do that. And I'm speculating, I've not done that, but it seems fairly obvious, okay? Okay, well, anyhow, all that aside, it's beyond the scope of our course to figure out what that is, and aren't you glad? Tell me you're glad, because I might ask you to do it if it wasn't. So, there's some complicated force going on while this thing's in contact with the table, right? And you could approximate it with this, that's fine. But, okay, again, come back to the idea that you want to use energy to do this. You can find the kinetic energy. I mean, you know, using this, you can figure out the time of each bounce, and you can figure out the speed associated with each bounce, the speed before it hits a tabletop, the speed after it hits a tabletop. But you can't analyze much about the actual millisecond or whatever it takes of all this thing's in contact with the tabletop, okay? You just can't do it. You could model it with more advanced techniques that I've mentioned, but you can't do it. So if you want to use force, you're going to have to use, you want to use energy, you got to have some information about force and displacement, right? Since you don't know the rule for which that tells you how this thing compresses, you're not going to be able to figure out the displacement during that interval, okay? You're not going to be able to use energy, although it's not a bad idea. You're not going to be able to get to the details that you need, okay? Now, you know, and I kind of had to fish it out of you, but finally somebody said, well, I said, what else do you know about this thing, okay? And, you know, after a few minutes, somebody said, well, you know, it's momentum. Well, bingo. And as soon as you mention momentum, we see that we can easily, if we get all this, if we do this analysis, if we have this information, we can easily get all the velocities and times, right? So we'll know when each collision occurs and how fast the BB was moving, and presumably we can find its mass with sufficient accuracy. And at that point, we can calculate its momentum before and after each collision, right? Which means we can apply impulse momentum. Okay, so I'll just say energies can be calculated So I'll say positions during collisions can't be calculated within the scope of the course and can't accurately be calculated or observed. With any method. In other words, there are uncertainties in your model, there are uncertainties in any observation you can make. So they prevent us from using the known energies to calculate the average force.